We're going to cover distributed loads in this lecture. So what a distributed load is it's a pressure that's applied across evenly or distributed across a section. Um, and these are very common in a lot of engineering structures or engineering machines. Some examples would be the load created by pressure within a gas or a liquid tank, the pressure caused within like a silo for like a granular substance like salt or sand or wheat. And then another example would be like the air or wind that causes a force, the drag forces that would go against like a sign or an airplane wing. So in order to, what we're interested in today is we're trying to take this distributed load or this pressure, and we're trying to simplify it down to a single point force. So for example, we have a very simple case where we have a cantilever beam that's supported by a roller on one end and is fixed at the other end, and there's a pressure that is distributed across the whole length of this uh, this beam, and we have the pressure is only a function of x, okay, and the width of the beam is equal to b. So we can simplify this down to be a 2D case where instead of having a pressure as a function of x, we'll define something called a distributed load, W of x. All right, and W of x is just equal to our pressure as a function of x times b, or the width of our beam. Okay. So, all right, the units of a distributed load are typically in newtons per meter or pounds per foot or pounds per inch. Okay, and typically they'll be drawn something like this. All right, so that's going to be equal to, all right, so what we're interested in is we want to determine where would be the equivalent concentrated force or the total force caused by this distributed load. All right, so we'll call that FRY. All right, and we want to know where would this force need to be applied. So at what point, we'll call that point x of c, such that it would create an equivalent moment equivalent resultant moment and equivalent reaction force at our support. Okay, so to determine the magnitude, so what we're looking for today is what is FRY and what is x of c. So to calculate what FRY is equal to, we can look at our diagram here, and what we can do is we can draw a small differential element dA that will be equal to, which we can write as being an incremental part of our total force, which we can write as W of x dx. Okay, so that's just the height of our distributed load at that point times the width of that point. So we can say that the total resultant force in the y-direction would be equal to the sum of all these smaller differential areas. And we know to take that sum of a continuous function, what we'll do is we'll take an integral. So we can say that FRY would be equal to the integral from 0 to L of Wx dx, and that would be equal to the integral of 0 to L dA, or just be equal to the area under the distributed load curve. So, all right. So, if you go to the next, so we have our equation for our resultant force. Now, the only thing we want to calculate now is our the distance, or where is that force being applied. So it would create an equivalent moment. So to do that, what we're going to do is we're going to look at our problem again, and we're going to say that the moment about the origin point at point O of our beam will be equal to the sum of all the moments about the point O. So in the case of our simplified version here, right, that moment would just be equal to minus FRY, magnitude of FRY times the moment arm distance XC. For the case of the left-hand side, the moment would be equal to X times our differential area term, which is equal to WX dx. Okay? And then if we integrate that across the whole length of our beam, we would get the total moment caused by our distributed load. Right? So what we're interested in is we're interested in just solving for x of c. So if we rearrange this equation and solve for x of c, what we end up getting is x sub c is equal to the integral from 0 to L x w of x dx over fry. And then we can plug in the value of fry from the last page. So if we just include that integral, you get integral of w of x dx on the denominator, and then the numerator would be the same. So you just have to evaluate these two integrals to calculate the x of c. Okay, so so the reason we're interested in this is that f of r and x of c would create an equivalent moment about our support, right? And then that equivalent moment and load we could then apply to the next rigid body and determine whether or not that rigid body would fail or not. Oftentimes, I know we just define these two integral equations, but often many distributed loads come in are defined, maybe defined using simple shapes. So what I mean by simple shapes is like typically it's like a triangle, like they can be triangular, they could be rectangular, they could be parabolic, right, etc. Right, and then to calculate, so if they're a simple shape, we can use tabulated results. So we can say that FRI, RY would just be equal to the area under these curves, and then X of C would just be at the centroid of these areas. So for many common shapes, what you can do is you can look up the centroid on this table here. So if you have a centroid of all these different types of shapes, circles, squares, parabolas, etc. All these tables include the centroids of all these different types of shapes, and where the areas of these shapes. So for a triangle, for example, this would be FRI would be equal to 1/2 times the base and times the height of our triangle, and then the centroid would be 1/3 from the base of the triangle. So you could use this to get x of c for the triangle here. Okay. All right. And that concludes how you can determine the centroid of where your distributed loads, what is your equivalent force for a distributed load, and where would that distributed load be found along your structure.